When I read the bio of our next presenter, it seemed quite a motivational road to where he is currently, given that he started off his career as an electronic technician way back in 1981. A native Jamaican, Mr. Lloyd Lynch completed his BSc degree in computer sciences and applied physics, and he was promoted to scientific officer with the additional responsibility to oversee the local operation. Mr. Lynch is now a research fellow at the UWI Instrumentation at the Seismic Research Unit and is currently pursuing part-time graduate studies. He is a member of the National Building Code, a member of the ODPM Risk Information Committee. He's also on the TNT representative of the Directive Council of CERESIS Regional Center for Seismology in South America. I hope I got that right. I hope I got the topic right too. His topic is entitled Future Radical Changes in Mapped Earthquake Hazard Potential in the Anglophone States of the Caribbean. During the break, when I looked at the word Anglophone, I was wondering, what is that? But it really means English-speaking states, right? So without further ado, I present to you Mr. Lloyd Lynch.
Good afternoon. Good afternoon. Thank you, thank you. Protocol being observed. Let's jump right into it. I have about 30 slides, so I think I'll have to go very fast. It will be like, huh?
You got this slide, right?
No, bring it up for me, please. It would be like drinking water from a fire hose, one that's pressured. But while they're putting the slides together, I'd just like to commend the last speaker and say that, you know, we at the Seismic Center have worked with the ALNG company, and we do admire how the prominence that is given to safety. It's one of the, well, I think it's the only company that provides a post-seismic inspection system for the North Coast Marine Area pipeline, in which the design is such that if an earthquake that produces certain ground motion occurs, then the Seismic Center is contracted to inform the platform, and they'll shut down the flow of gas and send down a submersible. Also, I've been part of the team that reviewed the seismic hazard design assessment when the ALNG plant was being built. And the actual work was done by Fargo West. And they actually did quite a good job. They were quite conservative in their design. They recommended that because of the uncertainty of the Los Bajos fault, the uncertainty of the activity, they recommended that we continue to monitor. And ALNG has obeyed pretty much. And today, we still have a microseismic network in that region of the country. So they do pay a lot of attention to safety, and this is good. To add to your presentation, when the space shuttle was designed, it was the chance of a crash was assessed to be about 1 in 100,000, and Columbia failed on its 17th voyage. Good. So you need to pay attention to these high consequence, low probability events. So let me go on into my present. Black swans. Okay. So, now, this earthquake phenomena is one that is poorly understood. In the last couple of years, since, well, 2010, we have had quite a few significant events. Back when we had the Martinique earthquake, we had a comment, well, the Antigua Sun interviewed the head of the Antigua Engineers Association, Mr. David Hadid, and he said that based on the minimal infrastructural damage resulting from the major earthquake in 2007 and the island's stringent building code, Antigua and Barbuda should aim to ride out a magnitude 8 earthquake pretty well. Good. Most recently, we had that event October 13th, and the CEO of the ODPM said there were no reports of any damage from Friday night's earthquake. He said no reports of damage after an earthquake of this magnitude showed that the country has good building stock and that the country is well prepared for any disaster. Good. So I am not putting this there to discredit anyone or anything like that. Sometimes the media do put you on the spot. But surely people in these sort of positions should be sufficiently informed to make, more informed public statements. But earthquakes are poorly understood, so I do understand the position. So in this presentation, what I'd like to do is to show a number of slides that will provide a better understanding of the phenomena. So with regards to the magnitude and the distance of the event, this slide shows a number of earthquakes that have affected Trinidad and Tobago. So this axis is the distance from the earthquake to the source, where it was felt. In this case, we're talking about Port of Spain or Tobago, Scarborough. And this one shows the energy release in the earthquake. Above some of the earthquakes, you'll see the intensity at which it was felt. So most of the events that we have had in Trinidad and Tobago, near Trinidad and Tobago, occurred offshore at some distance. So they were not quite destructive. So most earthquakes tend to be destructive if they are very large, like this one, 1766, a magnitude 7.8. It was roughly 100 kilometers from the coast, but it was felt at intensity 9, damaged most of the buildings that were in place at the time. We have also this one, 1888, intensity 7, caused a significant amount of damage. Also in that same zone, it was the same zone that caused the earthquake back in October, offshore in this region. Good. So the further away you are from an earthquake, then the lower the ground motion. So it depends on the size of the earthquake and the proximity to the event. With regards to Dr. Ramroop's comment, research is actually showing, this is Dr. Richard Clark's research here, that the building stock, the predominant building residential houses in Trinidad are likely, there's a likelihood of 0.45 to 0.6 chance of them collapsing if the ground motion that we design for actually occurs. That's about 0.3 or so. Our 475 return period maps prescribes this sort of ground motion. If we do have an event of that size, then there is a 45 to 60% or 65% chance of collapse. Good. So I pointed out that the ground motion is highly dependent on the attenuation relationship, the distance from the source. And this is what a typical set of attenuation relationship looks like. We call them sometimes ground motion prediction earthquake equations. Good. Tend to fall off rapidly near the source, and then it sort of tapers off more gradually as you move away. So most events tend to do a lot of damage within 30 kilometers of the source. Good. So over the years, we have produced seismic hazard maps. The Seismic Research Center started in 1954, and we have been given the mandate to produce maps. And these are examples of some of the maps that we have produced. What you can see from this map is that is the evolution of the seismicity. For example, this first map of Trinidad and Tobago, the peak ground acceleration was concentrated, or the density function of the ground motion was concentrated in this area, that hotspot source zone of the Paria Peninsula. But 10 years later, this is Trinidad here, we see some activity in this region. That was in 1988 earthquake. You also see from this map that there is some sort of evolution in the methodology. So in the first two maps, these were PGA maps, peak ground acceleration maps, whereas here we adopted the IBC, the International Building Code, and here we produced spectral acceleration maps with 2% probability of exceedance in 50 years. These were 10% probability of exceedance in 50 years. So those are some of the challenges that we have been faced with. The most recent maps is this particular one is not as complex as the other because we didn't map the offshore regions, but it's a lot more complex. The methodology used is a lot more complex. And over the years, we have also seen an increase in the hazard. Good. So going back to the topic of my talk, radical changes in the mapped earthquake hazard potential. The primary drivers for this are the lessons from other tectonic regions of the world, like the Tohoku earthquake and the Sumatra earthquake. Then the growing body of geological and geodynamic research that's taking place in the Caribbean. And thirdly, higher demand for safety as advocated in new building codes. So let's deal with the first one. This is a plot of a large number of earthquakes that have occurred over the years. It's taken from a researcher by the name of Roger Bingham, University of Colorado. And it shows a plot of the earthquake magnitude with the deaths per earthquake. As you can see here, earthquakes of magnitude 5 have killed quite a number of people. 6 also. It all depends on the proximity to populated center. 1972, for example, the Managua earthquake killed, it was about magnitude 5.5. It killed about 12,000 people. What I want to draw your attention to is these two earthquakes, the Sumatra and the Tohoku, Japan. These are both magnitude 9+ events. The death toll from this one was about 220,000, whereas this one about 22,000. Those two events shattered some very important hypotheses on which our hazard maps were based. For example, the Sumatra earthquake, we had a number of different segments along the tectonic regime rupturing concomitantly. And that's what led to the magnitude 9. In the Tohoku earthquake, it was also thought that that region couldn't generate a magnitude 9. Good. In the early days, there was a very strong paper which suggested that the magnitude or maximum magnitude of an earthquake is highly correlated to the age of the crust. And that paper was well cited, and a lot of tectonic researchers in various tectonic regions based their maximum magnitude on that. These two events shattered that. So in the Caribbean, we are revisiting that to see whether we can get higher magnitudes than the 8, which we had our maximum magnitude set at. And there are some clues that this may be so. Back in 1812, we had a magnitude 8+ event in this region. The Bocano Fault in Venezuela and the San Sebastian Fault ruptured. I think about 40,000 people got killed in that event. Good. One behind the other. It's the largest event in Venezuela so far. Within a few days, the St. Vincent volcano erupted, so that was a strange one. Also, as I pointed out before, we are seeing knowledge is increasing in the region. This map, for example, is the Jordan map of 1979, the seismotectonic map. It has gotten a lot more complex now. It's not just one plate. There are several microplates as shown in this map from DIMETS. So we have increased our knowledge of the region. Another clue is that we have seen in the past where a number of events have clustered, large events. Good, like for example, 1843, the largest event in the Eastern Caribbean occurred, a magnitude 7.8 near Guadeloupe. And 4 years before that, we had the Martinique event at 7.5. These are two large earthquakes. 4 years apart is a very small, like a few seconds geologically. So what happened in Sumatra, Martinique is quite close to Guadeloupe, pretty much happened there. Good. Something similar happened in this one. I'm trying to rush here now because I realize that I'm running out of time. Moment accumulation and release. It's the large earthquakes that actually diffuse the bomb that we are living on. Good. It takes about 100 magnitude 7. 100 magnitude 7 to equal the amount of energy released in a magnitude 8. Good. So this map shows the moment release. Think of moment as energy pent up. Between January 1906 to 2005, and that's the global figure. Chile, 1960, that's the amount of moment it released. Magnitude 7 to magnitude 8 all over the world, and so on and so on. So it's a big earthquakes that release the moment. In the Caribbean, we have had a large event. The large events that have occurred in, say, the last 100 years are the two that I just showed, Martinique and Guadeloupe. Then we, about 100 years before that, we had the 1766 in Trinidad. So particularly in the southeastern Caribbean, there's a lot of moment accumulation. And this moment is going to be released one day. Good? How am I doing with time? 2 minutes? Growing body of geological and geodynamic research. So here we have the contemporary seismicity. The center has been in operation for 60 years. That's a very small amount of time geologically. Good. Historically, we have about 500 years of data. Good. This is the distribution of the events in the historical period. But the seismic cycle goes back to thousands of years. So our hazard maps shouldn't only be based on the contemporary seismicity and the historical seismicity. We need to go back into the geologic record. And this has been one of the drawbacks of the hazard maps that we have been producing at the Seismic Center. A typical example of hazard maps that is based on contemporary seismicity and historical seismicity is this one that was done for Dominican Republic. It was done by a group called GSHAP back in the early 90s. And this is what happened in the Haiti earthquake. As you can see, the energy release or the moment release was in a region that was not shown up, that didn't show up in the hazard map. Good. After the Haiti earthquake, the USGS and some other researchers have gone in and they have mapped the faults, and the hazard maps are now more based on geology and the geologic potential, and this is what the map looks like. You can see how they tend to, the contours tend to hug the faults. Good. So in Trinidad, we have identified that there are a number of faults, and through geological and geodesy and so on, identified that the fault that is accommodating most of the strain between the two plate boundaries is the Central Range Fault. This is John Webber's research, and we have a number of continuously operating GPS reference stations that are operated by the Ministry of Agriculture and ourselves that are showing that the north of Trinidad is moving off east in the Atlantic at a much faster rate than the south of Trinidad. And this is happening around the Central Range Fault. Good. The faults have been mapped extensively, and they are quite extensive. That Central Range Warm Spring Fault, for example, extends off into the sea and on the east and also on the west. There was an experiment back in 2008, a collaboration between the Venezuelans and a number of universities in the US, and they have shown that the Central Range Fault goes down to about 10 kilometers. They ran a number of ocean bottom seismometers on the floor of the ocean for about 2 years, and they have done some explosions and have, produced some velocity models as well as fault interpretation. So this fault is definitely the most prominent, and as you can see, there is an arrow there, so there is some component of thrust also. Good. So we have the length, we have the depth, we have slip rates. So we can now incorporate this into our hazard maps. Good. Using Wells and Copperfield. Good. In addition to that, there is also another body of research. For example, this paper showing that there are a number of huge landslides of the continental shelf that could only have been triggered by large earthquakes. We have had paleoseismicity showing that larger earthquakes have occurred in the region in the, as recent as 500 years before present. And I think I have about 3 slides left. So in recent times, say the last 15 years, most of the shallow earthquakes that have occurred on shallow faults like the Central Range have shown to be very, very destructive and costly. You have like the Armenia, 1988, Northridge, the Izmit in Turkey, and so on and so on. Very expensive. Kobe, 120 billion in losses. We need to learn from these earthquakes. some of our recent events have been quite expensive. Tobago in 1997, 18 to 25 million. They haven't even repaired the libraries yet that was destroyed. We've had Martinique in 2007, 20 to 30 million euros. Haiti, $12 billion. Good. That's the casualty of Haiti. These are the cumulative death figures from previous events. So you see we have gone off the scale. Good. And just to put things into perspective, Trinidad is a small nation. You have a source zone that is running right through the center of the island. No. Good. Our previous hazard assessments have been based on sources that were offshore, several kilometers offshore. Now the source is right in the center of the country, and we just cannot continue to ignore that. What we are showing here is the intensity distribution of the Haiti earthquake, a magnitude 7. What I've done is shrink Trinidad to the scale of Haiti. Good? So this is the area that was affected, and this is the size of Trinidad. This event that occurred in Costa Rica, same sort of thing. Good? And to sum things up, we have a lot at stake. This, for example, is the gross capital formation of TNT since about the time that I arrived in Trinidad. That's when they were building the Hall of Justice and so on. If you take the gross capital formation is what you spend on infrastructure and buildings. Good. So when you add that up and you correct for inflation, we have spent about $1 trillion. That's what is exposed. Good. And we are a country without a building code. The engineers in the US cater for about 10% loss in an area that's affected by a large earthquake. So, and they have building codes that are enforced. Good. So you can imagine what could happen in Trinidad if we have a large event. Good. Thank you very much.
Thank you very much. Thank you very much, Lloyd.
So we have room before we go to the break for a couple questions again. And does anyone have questions? Fazir?
Thanks. Yeah, the 1766 earthquake that destroyed St. Joseph, do we have any idea where it emanated?
Yeah. It's just up north of the Paria Peninsula. It's the same sort of region that generated that event on October 13th, Friday, October 13th. Let me back up. What's going on here?
And a follow-up question to that is, are there any events documented that one can attribute to the central fault?
Are there any?
Any events documented that can be attributed to the central Los Bajos fault?
Great. The first question. Well, yeah. In this region, north of the Paria Peninsula. It's a deep source. What the tomography has shown is that a portion of the South American slab has detached and is sinking into the mantle. So from time to time you get these episodic, normal slipping, normal faulting. Good. So it's the most active zone, and the maximum magnitude is about 7.8. Good. What is important about engineering in South is that, or in Trinidad in general, for high hazard facilities, is that it's a complex zone. It's not just a strike slip zone like in California. You have subduction taking place, you have strike slip, and there is also evidence that there is some collision. So you have thrust events also. Good? So if you take, for example, build a structure in Couva, for argument's sake. Good? What you need to do is to do a site-specific hazard assessment in which you look at the contribution to the hazard from the various sources. So like, for example, this is a deep source, so the waveforms emanating from it at the source are going to be rich in low frequency. Good? Whereas, if that event is sufficiently close to the central range fault, and there's a rupture on central range fault, then you're likely to have a phenomenon they call fling, in which, or directivity, in which if the rupture is long enough, the shear wave velocity as it ruptures, the rupture velocity as it ruptures catches up with the shear wave velocity. That's a movement of the waves. And you have an effect which is equivalent to sonic boom. Good? It's called super shearing. And that can give rise to about 2% higher accelerations on your spectra. So you have to take care of that. What's important about that is it tends to be low frequency. So you get a huge low frequency pulse, which is very difficult engineering from an engineering perspective to mitigate. So you need to do a site-specific hazard assessment, look at the contribution from different faults, disaggregate, and even, well, get some accelerations, some time histories, and when you do your design, use them to test your design. So it's very important to do that.
So fortunately, we have a break coming up, Fazir, and you can engage Mr. Lloyd.